Hello, I'd like to introduce Theo Schlossnagle, CEO and founder of Sarconis, which does some really cool metrics and analytics work. Theo has hacked on a variety of operating systems, both user space and kernel space, and today he'll be talking to us about distributed tracing. Originally we had Scott Long scheduled to speak, but unfortunately Scott could not make it, so we ended up getting a better speaker anyways. So.
Ouch. Oh, man, I should tone down my performance, give them a better chance. Yeah, so as Sammy said, I've hacked on a lot of different things. Could be funny stories like I went to go build an in-kernel SSL implementation, but it was already there because I was running on Illumos. It's like, darn. But I'm glad to see that Linux has it coming. This is good. I think the one from Illumos, Solaris, was from the Solaris 2.6 days or 2.7 days, which is like 1999 or 1998 or something. But I played mostly in the, try to stay out of VM systems because they're horrible, in the scheduling space and the networking space and in the IO space. But my background is in distributed systems. So I studied for far too long at Johns Hopkins in the Center for Networking and Distributed Systems there, worked on networking consensus algorithms and resource allocation and high-frequency systems. So what back in the old days was the precursor to load balancing. And basically got kicked out of that program and decided at that point that distributed systems suck, and that I don't ever want to have to deal with those problems again because they're really hard to reason about. So then I went into work at high-performance websites, and everything was distributed systems again, so I got screwed. So one of the things that's really interesting, though, having been on all of the layers of the stack, and I say all of the layers, I don't mean all of the layers. I actually have never had the distinct, horrible privilege of programming firmware on disk drives or anything like that. But I've done a lot of kernel work, and I've done everything all the way out to like JavaScript in the browser and CSS and things like that. And you could say that they're awful, but when you need that mental reset, it's really good to just go and move something 2 pixels. It's just such a fascinating, like, oh my God, I did something productive. But one of the things that I found in all the work that I've done is that most systems, some of us have the privilege, I guess, of having blinders on and being able to work on one tiny little bit of the system, right? So you're like, you work on a memory system allocator. But I'm sure as the Facebook guy before me will tell you that when you're working on a memory system allocator, you're actually trying to deliver a web page faster to somebody, right? Like there's a bigger picture here. There's a full stack, and the more integrated you are with that, the more you understand what you're working on, like what value it has, and you need to be able to measure that end result. So in order to make performance really matter in organizations, the idea of like over-optimizing these micro benchmarks and things like that is actually really lame. It's really, I mean, I guess it's a fun masturbatory exercise, but it really doesn't get you where you want to go as an organization, right? It doesn't actually deliver better product faster to users. So if you don't care about performance, you should go, because it's the wrong talk. But performance from most of the people that I deal with actually deliver product over the internet to users, which how many people here do something like that, where they deliver, it's only half, that's much less than normal conferences I see, or the other half doesn't have working arms. But how many people here build a product and they don't know how the hell somebody uses it? There's got to be some people, yeah, okay, sort of like that. A lot of this stuff actually applies with just word massaging, right? So like on the internet, performance really matters because it improves user experience, which increases loyalty. It reduces product abandonment, right? It keeps users connected with your product in a way that they continue spending money, increasing revenues, building your staff out, having awesome company. And that's really the same when you ship products as well. It's not really that different. So one of the things that's really important when you talk about performance is having consistent terminology. And I apologize in advance, sort of apologize. Warn, it's trigger warning. There's a lot of meat and a lot of alcohol in these slides. Because I always, if I'm not measuring something in terms of meat and alcohol, I am rewarding success with one of those two things. So this is a wall of scotch. This is a happy wall. There is bourbons and whiskeys. I'm using that term loosely. But there's an interesting conversation that has to happen about throughput versus latency. And I'm sure everyone here really understands the difference. It's a well-positioned crowd to understand performance trade-offs. But throughput and latency are very, very different things. And when you're talking about most applications today, no one cares about throughput. Throughput is totally your problem behind the scenes. Every individual person cares about latency. So latency is often the one thing that you struggle with the most because the speed of light actually matters a lot there, as we talked about earlier today. And it's the one thing, as Artur Bergman of Fastly says, latency is the mind killer, right? It's like the one thing that you just can't hack. It's hard to hack latency because you end up having to ask a question of somebody somewhere that's not here, and then you have to send light there to do that, or some suboptimal version of light like electricity. So latency really is the focus of all the performance work that we end up doing. Throughput is really an afterthought. There are rare circumstances where that's not true, but it's a really different environment. I love this picture. This is my daughter in Germany. She's standing next to this. I don't know who made this backpack. That is awesome, right? I mean, she's not a small girl. She's 5'3". So that is optimizing for throughput, clearly, because that is a latency problem right there, right? Nobody can get anywhere they're going quickly with that bag. It's the whole tapes on a semi-truck at 70 miles an hour argument. So how do you measure time? And there is one cardinal sin of all of computing is that people somehow use measurements other than seconds. Should always use seconds, okay? Nanoseconds are seconds, right? They're nanos of seconds, right? Minutes are not seconds. Minutes are 60 times something, right? And hours are 360 times something. Days are 86,400 times something. Those are not fun multiples. You should always use seconds for everything. So when someone says, oh, you know, I do 300,000 requests an hour, you can go, but how many per fortnight? Right? Like, that is a horrible divisor. So come back and use seconds. And if the numbers get weird, and please don't use like megaseconds, because now you're an idiot. So keep things in seconds. And always make sure that you have sufficient precision to really understand the performance improvements that you expect to see. So the idea of measuring web performance in integral seconds would leave you squarely in like 1996. Where like my web page takes 8 seconds or 7 seconds. Web pages are faster than that. Typically, you don't measure them in sub-millisecond times, but you have to have them in at least milliseconds or microseconds. And what I've noticed is that there seems to be, from a coding perspective, like if you look in a lot of measurement classes for timing measurements, if you look in Go, you look in Java, you look in C, almost everybody is just universally using nanoseconds. So at least we bought ourselves 5 years, right? And before everybody's like, oh, I need a floating point number of nanoseconds because I only have half of one. But nanoseconds seem like a really good bet for now. It'll last you a while. So now that we can talk about time, does anybody know how long it takes for a user to get pissed off at your website when it's too slow? There's a magic number. What's that? A quarter of a second, 250 milliseconds. That's very close to the research that I read. I read that at under 200 milliseconds, the user can't tell the difference. Basically, it can't tell the difference between 1 millisecond and 200 milliseconds. There's just really no reaction time difference of that. And then anything after that, so 250 milliseconds to 300 milliseconds, basically you're the worst thing ever created, and they're looking for another product. One of the things that's really interesting is that when I started computer programming, I guess when I really started, I was writing a data structure in C, and it was crashing, and I used printfs because those are the only real debuggers. But But immediately after that, you start working on a kernel, you start working on a user space app. Eventually someone throws threads at you and you're like, why did this happen to me? But it was still running on a single system, and at least in the old days, a single CPU. So you had this kind of forced serialization pattern. It was easy to reason about those systems. There's not a system today that runs on one CPU, let alone any real systems that run on one physical system. And most run in systems that are at least 2 milliseconds apart from each other, right? So if you have a large system and it needs redundancy, you're going to be in a place where if a nuclear warhead is set off on one zone, that it doesn't take out another zone, and that happens to be about 2 milliseconds of light apart from each other, right? Or 1.5 milliseconds of light. So need at least what, like 60 miles, 80 miles, something like that between the two of them. So now you're talking about lots of computers, lots of CPUs. You have all the coherency problems you have on a single system, but now they're spread out. So you have clusters here, you have clusters there, you have coordination issues. And it comes back to like one of this thing where you're trying to convince yourself that this is a good idea to even be in this industry. And you're trying to reason about it. And I remember what one of my, I was a musician in a former life, and amateur musician. I never went pro. But I was told the real beauty of music is the space between the notes. It's not the notes, it's the space between the notes. That's what everybody is anticipating, right? You're anticipating the next note because there was space. So every time I want to throw my computer off my desk and flip my table and drive my car through the office wall, I'm thinking, really, this distributed system I'm trying to troubleshoot is beautiful because of the space between the systems. Like all of that time between when you sent something and someone else received it, and that argument that there is no clock. There really is no clock. Before you had one clock, and it could be wrong, but at least it was one. Now you have two, and they never say the same thing. So you have these really big problems. And performance in general is about how quickly you can complete some work, but when the system is disconnected, this idea of end-to-end latency might be easy to reason about, but the individual work units that happen are very, very difficult to reason about. From a correctness standpoint, which I won't really talk about past this moment, it's almost impossible to reason about, right? So if you're looking at a distributed systems algorithm like Paxos or something like that, and you're trying to deconstruct why something went wrong, pretty much the worst thing you can ever do is just look at a packet dump and try to figure out what happened. Mainly because you can't see the internal consistency of each node, and you can't see the clocks and their ideas of what's going on. So you're basically just trying to reconstruct an absolute shitfest. So what you end up having to do is model the algorithm and then look for holes in the algorithm. It's a much more theoretical exercise. Performance, luckily, is not that bad. But before we start measuring performance on a high level, I'm surprising you guys, this is not really a systems talk, is it? You're like, what the hell, when is he going to talk about something detailed? It may not come. But expand your horizons a little bit. One of the really important things that's missing in a performance culture is the idea of celebrating performance improvements, especially across teams. So I'll get into some anecdotal cases of how we fixed some performance issues that we had. But the idea of like, when you get a 2% performance gain, if they came every day, you know how compound interest works, you would have the fastest shit in the world. That doesn't happen, right? A 2% performance gain or 5% performance gain or a 0.5% performance gain is something worth celebrating. This is how I celebrate, you know, that's a good Lafroig and a steak and butcher's paper on the office table. That's how that works. You can each do it your own way, but I would suggest that you do it as a team, right? So reward your fellow colleagues and make sure that you have a performance that rewards performance improvement. So this focuses on small individual wins, right? The 1% here and the 0.5% there, and then more collective wins where you have teams. And I think that, like music being, the beauty of music is the space in between the notes, the problem with distributed systems is that the most likely place to optimize are the spots between the two systems. It's the place that nobody owns, right? You run your little REST-enabled microservice here, and I run another one that consumes from you. And I can make mine fast, and you can make yours fast, but we have to actually work together. And that ends up being a really hard problem. So those should be rewarded better. So the question is how do you have tooling that helps you do this? And that's really what this talk is about tooling. So Google came out with a paper called Dapper. It's actually quite old. I don't remember what year it was released in. It was 2008, 2009, something like that. If you go to that link, I'm sure it'll tell you. I didn't before the talk. But as usual, the code for this thing didn't ever see the light of day. And the reason for that is probably a really legitimate reason, in that it probably stored all of its data in a database that's not public, and it collected it off of systems that aren't public. So the idea of like releasing this like little snippet of non-functional code probably wouldn't make sense. But the paper was released and talked about how they did everything. And this is what architectures really look like a lot of times. That's a lot of lines. It's really hard to reason about these sorts of things. This is what our Sarconis alerting platform sort of looks like in its simplified form. It's a little bit more complicated than that. They've probably 5 or 6 different other systems in there that are running network accessible services, whether they're REST or not. So how does Dapper work? So the idea really focuses on this concept of user interactions, and the concepts are applicable for a lot of other things, but it's really easy to think of in the concept of a user interaction. So I come to a website. In our case, we collect data and then we show it to people and do analytics on it and do alerting and all sorts of really cool stuff. But someone comes and wants to see a graph of something. Right, so they're going to load a graph. They send a little JSON request. They have the little web app here, and they send a JSON request that says, I'm looking for this graph from this time frame to that time frame with this sort of analytics overlay. And it sends it off to our server, and then hopefully like 400 milliseconds later, 500 milliseconds later, it comes back complete with all the data in it. So we don't really hit 200 milliseconds, but people aren't running away. Helps that our competition takes like 14 seconds to do it. The idea is that I want to be able to trace the performance boundaries of everything that's involved in satisfying that high-level request, the one that's going to keep or lose a user. So the idea is that when a new request comes in, it comes into the load balancer, it's an HTTP request. Those are really easy to reason about. It may be a horrible protocol because it's text-based and you have to search for line endings and parse things. Really horrible. But it's also text-based and has line endings in it, so you can read it. So it's got a GET, it's got some headers. The idea here is that when that request comes in, I'm going to generate, possibly, a tracing ID for that request. And in Dapper, I'm not sure that it's completely clear, but there's an open implementation, which I'll get to. That's a 64-bit trace ID. Signed 64-bit trace ID. Who's the idiot now? All right, the person who you did their prototype in Java, that's who. So there's a 64-bit trace ID that can't be negative, a signed one. So it's really 63 bits, right? I mean, like, I don't know why people. So the trace ID comes into this one request, and as that gets passed back into the service, there are ways to encode sub trace IDs, basically these span IDs, into all of the other like network-based calls that you'll do. So as a new trace comes in, we get a trace ID. As we start and stop work, usually remote work, we will assign a new span to that work. And if anybody here ever seen a waterfall graph for a browser where you've seen the pages load and you've got the okay. It's an enlightening experience when browser, like web developers, have cooler tools than we do in systems. So sort of what it looks like here. So web request comes in to the do magic URL because that's what we all really want to do. And what happens is we create a trace ID and a span ID. And in the case of the first one, the trace ID and the span ID are just the same because I didn't have a subspan or anything like that. And there are basically 4 major events that happen on any span. So there is a SR, a CS, because why would you spell things out? I have no idea. An SR and an SS. So this idea of the initiation from one end, starting this work, the reception and acknowledgement of that work, that I'm going to start that work, then when I finish servicing the work, and then when the other end agrees that I've finished serving this work, right? So there's the round trips on kind of both ends of this span. So what happens is, as I get this do magic request, I decide that I actually need pixie dust to do my magic. So I go get pixie dust. And when I do that, I create a new span for that work. So now I have my trace ID, which is T1, and my span ID, which is T1. But now I'm the parent. So my parent ID is T1. I create a new subspan, which is T2, send that back to the next server. It does the exact same things with it. If it's going to do sub requests, it kind of goes, I'm the parent, you're the child, and creates this sort of thing. It does what it wants to do. It responds back. And the servers in here are responsible for emitting basically log messages around this stuff. And log messages are horrible. We'll get to that in a minute. There are a lot of flaws with this implementation, probably flaws that Dapper did not actually manifest. So what we'll see is something that actually looks like this, which is kind of useful. So this idea that I have, you'll notice that we don't actually have an explicit CS here, right? So I don't actually know when the browser thinks it's sent the request, because it doesn't play our game, right? So the CS here is kind of unknown, but then once it hits our front-end service and the trace ID is assigned to it, I now have a server receive event. And then it does some work, and it's about to initiate some request to service 2, so it says, I'm going to be a client now. Here's a client send on the new span. Then that service picks it up, has a service receive on that, service send, and then client receive on the other end, and then we send it off. And we also don't know when the browser is actually happy with the response. So those two little outside spans on the top level span are always busted. So really what the beauty of this is that Susan, who owns Service 1, and Bob, who owns Service 2, who never before could talk about the space between their products, now has a shared visualization where they're both accountable. And that changes everything, right? It changes the dynamic of how people can work together. They're actually looking at the same data. They're producing the same thrift messages. Horrible, horrible protocol. God. Java. Did Java ruin anybody else's life? Come on, some hands. It's only like 8 hands, you guys, man. I'm not saying it's a bad decision. That would be against the code of contact. I'm just saying it ruined my life. It's different. So the idea here is that now, before in those systems, we had network teams that were always responsible for the interactions in the spaces between applications. And I'm sure no one will raise their hand that they've pointed their fingers at a network team and said it's their fault, of course. Because who else are you going to blame, right? Yourself? Susan, who you went out to lunch with? That's not going to work. So what this does is it really allows, because of the increased visibility, it allows these teams to all look into each other's products the correct way. So now NetOps can actually get up in your product and look at the differences between your client send and your server receive. See what you've observed there. See if they can observe the same thing with packet introspection or what have you, or kernel introspection using dtrace or eBPF. And you've got your teams that can sort of reason about why they're taking so long inside the spans of their own delivery as well. So, pseudo-Dapper, which was called Zipkin and developed at Twitter, and then the guy who developed it left and it kind of went dead. And then I wanted it, so I implemented it at Sarconis and gave a talk about it at CraftCon. And then Adrian Cole, who started it at Twitter, is now at Pivotal. He picked it back up and called it OpenZipkin. And now there's a small community around it. So kind of a long 2.5-year process of getting it out into the open in a way that a community could get behind it. But basically, Twitter wanted to re-implement Dapper because they have all sorts of weird microservice challenges, and introspecting performance is really important to them. For some reason, that didn't thrive at Twitter proper, but it is alive. You can go download it. It's on GitHub. If you go to github.com/OpenZipkin. So it has some really unfortunate user experience issues. The UI UX is really, really horrible. But the concept is really simple. And it's really sound, and it's really valuable. We found it incredibly valuable to implement. But I will divert and say that thrift might be bad, but when you try to stick thrift inside thrift for the purposes of scribe, you want to burn your building down. So thrift is bad enough on its own, but scribe is a is a client service, a request response protocol that is thrift encoded, where people send thrift messages in the thrift encoding of the protocol. So if you're into user space to user space copying and for loops, that's great. I'm usually not into that so much. Performance-focused people tend to not use strings for that. So one of the things that we found was that was horrible. I love this one. Put thrift in your thrift. It's horrible, such a horrible protocol. In our screw scribe project, which apparently wasn't allowed to be called screw scribe, is actually called FQ to scribe. So we have a brokered message queue that we wrote originally at OmniTI, and now we maintain it at Sarconis, called FQ, which F and then a lot of like cartoon things and Q. I could say it's fast queues, but that's not actually what it is. It's more of an anger thing. But what it is it does, the idea of doing wire speed messaging, brokered wire speed messaging where you have introspection on that. And it also has asynchronous lock-free publishing of messages. So one of the really critically important things about observing performance is that the best way to have all of the instrumentation that you've put into your product ripped out is the first time it causes a production outage. Someone on staff, probably above your pay grade, will tell you, I didn't want that in there, get that shit out of the product, I can't believe you took production down. So all you have to do is say, log something and have it stop on disk and drastically reduce your performance, or have some sort of client request protocol that's synchronous, and you will tank performance eventually in production. You will wedge. And then you'll have all your crap removed from the product, and then you won't be able to see anything. So it's incredibly critical for us that when we log, I would rather lose this information than ever have it prevent me from delivering product to a customer. So this sort of performance information is incredibly valuable to me, but not more valuable than delivering a good customer experience. So I'd much rather have the messages drop on the floor. Critical to us that all of that is non-blocking. So we have basically the way FQ clients work is that you have a single producer, single consumer FIFO, uses a lock-free data structure, and you take your message and you put it on the list and you walk away. And if you have more than a configurable amount, usually it's like 10,000 or 50,000 messages, you don't put it on the list, you just walk away. So you never really block as a publisher. You will have asynchronous issues and latency issues, but those are all well worth it to never really block as a publisher. But unfortunately, OpenZipkin requires scribe, so then we take FQ and we read off FQ, and then we like thrift as many times as required to jam it down another socket, and then it goes into FQ. So it goes into Zipkin. So Zipkin is written in Scala, as if there weren't enough problems already in the world. So it provides annotations for Java services and annotations for Scala services. So if today you have a Java app or a Scala app, it is in theory very, very easy to annotate your application for performance timings and have the Zipkin infrastructure that's written in Java kind of just like latch onto that like a leech and siphon that stuff off and publish all of that. So if you are running Java services, this should be an easy win. We don't tend to run too many Java services. We have some. We have a lot of stuff written in C. And actually, last year I presented on our time series database. And one of the things that we had done for that conference last year was we released our a development library open source. So we have a development library called libimtev, which is a multi-threaded eventing library. It's kind of like libuv or libev or all the other ones that are out there, except that it's got a lot more stuff into it. I won't say it's necessarily better, but it has a lot more things in it. It does resizable, manageable job queues, focuses on lock-free data structures. It has safe memory reclamation built into it. It's got all sorts of interesting stuff, and it supports ePoll, I think with the Thundering Herd problems, but it supports KQ and ports without them because they didn't have that problem. All these different systems. And in addition to that, it has built-in Zipkin over FQ publication support. So if at any point in your time in your application, you can just create a span context and then say, I'm done with this span, and we'll get automatically submitted into a fabric that collects Zipkin data. So if you're writing a C app and you want to do this sort of instrumentation, kind of comes for very low cost to the developer. We also wrote Perl support, which was just a fantastic exercise of the horrible, horrible things you can do with Perl. So we monkey patched everything, like DBI, memcache, and all that, and it was amazing. You just load this one Perl process, one Perl module, and it basically changes the behavior of every other thing in the system that talks over the network and traces them. And it was like, hey, you know, if we put a bug there, we screwed everything up. I don't think there are any bugs there. So, but that's also open source. So in the real world, what does this actually look like? So what you'll see, this is a little hard to read. I don't know if you can see the blue. A little bit, you can. Okay, so the subspans. So this is sort of what the thing looks like overall. Is that you have a large piece of work, which is the top line, and you can see in this case it's a URL, JSON graphs data in flight with a UUID on the end. And then I've got all of the subspans of work that happen on this. So I have a DB PG execute, so I'm executing a Postgres query there that took 1.19 milliseconds, and then later on in that stream, probably about 18 milliseconds in, I executed another one that took another 3.5 milliseconds. You can see this cascading like thing go on here. And that's basically what the interaction looks like to deliver this thing, which not only does it help multiple groups understand what's going on. When the first time a web developer looked at this, they're like, why the hell are we doing 3 database queries there? And I was like, oh, wow, so you didn't even know that. It's just in your app. It might have been me who said that. I don't know. But so each of these spans basically has, like I said, it has a client start, a client receive, a client start, server receive, server send, and client receive. In addition to that, you're allowed to annotate all of these different things. So for example, when a service call goes off, you can add, in this case, this one is the client, the Perl client that is fetching data from a time series database. I can see what line of code fetched it. I can see the URL requested. I can see the status, and I can see the node that it connected to. I annotated that stuff. So when you open up a span, you kind of get the whole parent-child relationship and the markers on the ends, but then you can add arbitrary key value pairs into that span. And those all get kind of bundled up in that thrifty object and get sent off. So now you have a lot of insight. So this is actually full-on network tracing. Not network tracing, networked application tracing. So then you start to see another sample from that after we fixed a problem like that. Now it does 1 database query instead of 3, radically better. Yep, let me flip that. So on the first day after deploying this, so what this takes for us, I don't think we do that many requests, but we're probably sending, I don't know, probably 10 gigabytes of traces per day into some Amazon node somewhere that we pay like $150 a month for. It runs a Cassandra node. Occasionally it gets full. Cleverly, someone rm-rf/data and then runs the install script again. Now we have an empty box running Cassandra. Like I said, the UI UX isn't great on the thing, so it's actually really hard to find specific traces. It's a lot easier just to go into the tool and say, over the last hour, show me the slowest 15 things, because that's really what the UI is designed to do. I hope that they improve that a lot. It seems like they're focusing on that on the project. But like I said, having the data is really useful, but it's definitely not more important than paying to have the data, because it's really expensive to collect it really safely and things like that. So we're very unsafe the way we collect it, and we're happy to throw it away and start over whenever we want. It's really a development tool more than anything. But on the first day, we noticed that in our distributed database, all of the configuration of the distributed database that has, like 20 nodes in it or what have you, has a topology, and that topology is a SHA-256 hash. And the client was calculating the hash wrong. So every single time it would go to the database, it would say, I need to go to the database. Let me figure out where the data is. Oh, I don't have the same topology as you do. You must have changed your topology. And it will go grab it again. So every time we made a request, it would go get the topology, compile it, cache it under the wrong key because it had an error, and then it would serve the request. And we were able to shave 350 milliseconds off of every single graph request. I mean, amortized off. We still had to compile on the first one. But that mistake, we found that in the first day. It was like the request took 350 milliseconds longer than it should have. And it was kind of like a big red spinning light on the graph. You know, you just look at this and you're like, I can't explain that 350 milliseconds. That's like a really long time. But having the right visualization made that make sense. And then on day 4 through 7, when someone went and looked at it, they noticed that some percentage of the time we had about 150 milliseconds added into every single request. And there was so I have been quoted before, and I stand by the quote, that hell is packaging other people's software. So every developer, every software engineer always thinks that they're smarter than the person consuming their product, and they always do something really clever, some clever performance optimization. Well, libcurl has this like built-in asynchronous resolver that misfires sometimes, and you have to like explicitly compile it out because I have a resolver that already works on the system. And so it was like 90% of the time, this thing would fire the wrong way. And it would introduce 150 milliseconds of latency while it tried to do an async lookup, timed out, and then use the system resolver. And then 50% of the page loads that we had ended up inducing that behavior. So we ended up having 50% of 90% of the time we had 150 milliseconds. And it was just looking at the traces and realizing, like, why does this same request, why is it 150 milliseconds longer here than there? And that view gives you a really, really clear insight to that. As I would say that the Zipkin stuff doesn't answer any questions, it causes all of the right questions, right? It shows you a picture and you will find problems with the picture and you will ask really good questions and you usually result in pretty epic performance gains in the beginning of that process. I highly suggest, I don't know what languages people use here, I didn't see a survey of that. How many people use C? Well, that's okay, that's good, that's my crowd. All right, Java? No, nobody's raised. Oh, he's bold after all my talk. Excellent life choice. Scala and Perl. Nobody. One finger. It's okay. 20% of the time. Not 100% of the time. 20%. Yeah. So I think that when you look at all the language platforms, the concept of microservices makes all this stuff a lot more applicable. And the idea of being able to stream all of this stuff onto kind of the same, into a single dialogue to have inside an organization across teams is really important. So go forth and build this stuff. It took me like a day it took me a long time to like instrument our libraries with that stuff. But since we've done it for C and you can just rip the code out, it's all BSD licensed. And then the Perl stuff should work with like anybody who runs Perl. That stuff's not specific to our platform. The Java stuff's already there. If you run any of those, it should take you about a day to get all of this stuff running in a prototype. So I think the future is really interesting. One, screw Thrift and Scribe. They're horrible. I just had a conversation through the original author of Zipkin to get the wire protocol and FQ kind of put back into the source tree. And in this awesome, fantastic explosion of open source governance, he was like, oh, I want to go do this. And someone was like, that's not in our backlog. You can't just go do that. And I was like, backing away slowly and looking for the exit. It was like, whoo. It's like, that's not how open source works. You know, you go do what you want to do. So that was really weird. I haven't seen one of those since some other Apache projects I had been involved with. So I think that from the Zipkin point of view, I think using some other wire encoding format other than Thrift, maybe something like Cap'n Proto or flat buffers or something like that might be appropriate. Right now it does millisecond level granularity integrally, which is pretty bad for anybody doing high performance systems timing. So nanosecond granularity would be really good. It would be really fantastic to have a set of audit or LD preload libraries for C programs that would actually automatically wrap things like socket connects and closes so that you could actually just magically handle all of that stuff. That ends up being a little bit harder without something even cooler, where I think the future of this might be IPv6. Because IPv6 allows arbitrary frame chaining, You could create a basically Zipkin or Dapper style trace header that gets injected in IPv6 sessions. So when I have an application that has a context for a certain, like I know what trace I'm in, I know what span I am in, I just called connect. That socket could say, hey, guess what? Let's ioctl this frame information onto that socket, and then that would be put in the framing information for IPv6, and it would just exist on the network. So there would be no inside the protocol augmentation for any of the apps. And you could pull it out the other side with an ioctl. I think that would be absolutely fascinating. Totally not what I'm going to do, but I think that would be a way to really get this ubiquitously throughout an entire complex system. But when I tell you that you actually have to sell somebody IPv6 to make it work, then you're like, oh, screw it, I'm out. That clearly did not work over the last 20 years. But that's it. I suggest you celebrate performance again with whatever whiskey that you like whiskey. So, does anybody have any questions? There's a question.
Okay, I'm from IBM. Are you familiar with ARM, ARM, Application Response Measurement? It's an open standard.
I am only familiar with the chipset.
It's pretty much this.
Okay.
I mean, you put hooks into the middleware, and you make measurements of response time, queue time, etc. And IBM middleware like IHS, WAS, and DB2 are all ARM instrumented. I actually would like to hear more about it, but maybe offline.
It'd be good. Yeah, I mean, if
It's the same idea.
if there's a way to serialize that into this format, then it all suddenly comes for free now.
Yeah. Another thing is, after instrumentation, of course, you have to collect this data, right, with an agent, I suppose.
In this case, you can't really use an agent to pull it out. You really have to have some sort of fire hose feed coming out.
Okay.
Right, because I mean, you're doing 100,000 transactions a second. You'd have to basically what we do is we have an outbound queue that.
I see.
Yeah.
What collects all? I mean, imagine you have a distributed application, on different servers, and you want to build this entire topology. How do you do that?
So they all have the same trace IDs. You know how they lay into each other. You'll get accurate timings on all the spans, but you won't get accurate offsets unless you have highly aligned clocks. So it's pretty darn important to have NTP or PTP running on the systems. But other than that, what we have is we have a mesh network of FQ daemons. They're super tiny. They take about 5 megs of memory total, and they can pass wire speed messages. And then basically everybody just dumps all of their Zipkin encoded messages onto that queue, and those all funnel out to a box that horribly is running scribe converter and puts it into Zipkin.
I see. Okay.
So, but that takes about, I don't know, less than 0.1% of the CPU on all the boxes.
0.1.
Yeah, it's very small amount.
When the server utilization is at what level? I suppose that as the number of transactions go up, the utilization of that process should also go up, right?
It
when
would.
You say 0.1.
I'd say like 100,000 messages a second, you're probably looking at certainly less than 1%. So usually probably in the 0.1 range.
Okay. Thanks.
It might be the reason we don't use FluentD for that, for example, because it's a little bit more expensive. Not significantly, but.
Hi, Theo. Are you using this primarily for network stuff, or are you also doing things like lock tracing? Because that would be super useful.
Lock tracing?
Yes.
We currently use it for really microservice level network transaction handoff. So I think it would be neat to. There's nothing that prevents us from doing like lock level stuff. I think it's just a weight of how much data output you expect to see. I mean, it is a lock. I mean, you do have to allocate the span. So there is a malloc involved. You could probably get away with that using a free list, but then there's a one lockless put onto the FIFO.
Kind of in the same vein, I'm curious, how hard would it be to integrate, say, perf events or dtrace events or whatever into this?
So I don't know enough about perf events. Dtrace events I'm very familiar with. The challenge, I think the short answer is that it could certainly be done if you're careful. The problem with dtrace events is that they are singular events, as opposed to this comprehensive time-elapsed span, start-finish sort of thing. I mean, there are ways that you can do like function boundary tracing where you do have an entry and a return, and there's a lot of apps like in Postgres, for example. The Postgres dtrace implementation actually has start and finish on the planner and the executor engine and everything like that. So you could do spans through that whole thing as well. I think the trickiest part there is specifically in dtrace is going to require a lot of dtrace foo to get the trace IDs in there and out of there again. Copying them in would require you to be in destructive mode, which is scary. Don't do that in production. And getting them out would be enough to funnel them into another process, but finding them in whatever protocol. So that's kind of the problem today, is that it's really easy if you have a REST API because you've got HTTP headers to play with. But if you're just doing like Postgres queries, you need to inject a comment in the beginning of the Postgres header that has your trace IDs, because there's no other way to put it somewhere, which is ugly. I don't have a mic to drop, but that's it.